Hi there, Ray here. How are we
Yeah,
doing? You're a
I'm
Trojan.
fine.
Have you just literally just walked into the house or something?
I just got changed.
Oh, okay. So you've had a bit of time to
Yeah,
have a 5 minute breather. Good.
yeah,
Okay. So we said we were going to revisit reversible reactions, didn't we?
yeah.
Good. Okay. So I'm going to firstly just give you some brief reminders of the main key points you're meant to remember, and then we're going to go straight into doing some exam questions to see how well you fare on those. Yeah?
Yeah.
Okay, good stuff. So if I have reactants here as A plus B, and this here is a reversible reaction, so I represent it using that symbol. It can go both in the forward direction, which is that arrow, or the reverse direction, which is this half arrow.
Yeah.
For this to take place, okay, for this reaction to be reversible, it must be carried out in a closed system. So what is a closed system? Can you remember?
Is it where no? Is it where no? Is it products or reactants? No, nothing can.
Can
No product.
escape, yeah. So
Yeah.
no reactants, you're absolutely right. All products can escape. Excellent. Good. So that's what we mean by a closed system.
Yeah.
And just to annotate this, oops, means reversible. Okay. Now, if this is a closed system and these reactants are forming these products, at some stage, the forward, or rather, should we say, when the rate of the forward reaction meaning forming products,
Yeah.
when rate of forward reaction is equal to the rate of reverse or backward reaction, which is this other half arrow.
Yeah.
Then we have said that at that point we have what is known as dynamic equilibrium. Sometimes it would just be called by the term equilibrium, but actually what they mean is dynamic. Why is the word dynamic used?
I'm not sure.
Okay, because the reactions actually are taking place.
Okay.
Both the forward reaction is taking place and the reverse reaction, but because they're taking place at the same time, we're not seeing any difference.
Yeah.
Okay, so reactions are still taking place, even though there is no change in the concentration. Are still taking place, even though no net change in concentration or concentrations of reactants or products.
Yeah.
Okay, so that's the next key point. Now, should we change any of or rather should we effect or should we apply a change to this system, this closed system, which is in dynamic equilibrium? That system will try and act against whatever action or effect we're applying onto that reaction. Okay.
Yeah.
So there's a number of things we might want to do. For example, we might change the concentration of A. If we change the concentration of A, well, this reaction is going to say, well, I want to get rid of that concentration. I want to bring it back to the original concentration A was at. So what it's going to do, it's going to have to remove A or reduce the amount of A because you're trying to increase the amount of A.
Yeah.
The only way this amount of A can be reduced is if more products are formed. So to describe that, because it's talking about products, we say that the equilibrium position shifts to the right, meaning this is the right side, meaning more products are formed.
Yeah.
If we said that the equilibrium position shifts to the left, well, this is the left. So you can kind of think about it as an equation almost where these products are at the left-hand side, and these are at the right-hand side. So we simply use that term to say the equilibrium position shifts to the right, meaning more product formed, or equilibrium position shifts to the left, meaning more reactant formed. So far, so good. Okay. So that is what Le Chatelier's principle states. Now, what are the things that can affect the rate of any reaction? Can you try and recall them?
The temperature.
Factors affecting reaction rate. Absolutely. One, the temperature, which brings me to ask, did you ask your teacher about that concentration question, or another teacher?
No, I haven't seen her since.
Not yet. Okay, good. No problem. I'm sure you get to it before the week ends. Okay. So temperature, anything else?
The concentration.
Concentration, correct. Anything else?
Is it like it? I don't know.
Surface area.
Yeah.
Because again, it's collision theory, so you've got more reactants available to collide with one another. Anything else?
Is it? I'm not sure.
Okay, pressure.
Oh yeah.
Now, pressure only affects reactions where gases are involved.
Yeah.
So if one of these things was a gas, it doesn't mean that all the products and reactants have to be gases, as long as there is one gas at either side, either on the left-hand side or the right-hand side. If there is a gas anywhere, then pressure will affect that rate of reaction. So it affects gases, because gases are compressible.
Right.
And by compressing a gas, you are increasing its concentration.
Yeah.
Because pressure means that you've got in a small, well, if you increase the pressure in the same volume or in a smaller volume, you have more particles compared to decreasing the pressure, which would mean that in the same volume, you'd have less particles. Okay. Right. Anything else?
Is it like if there's a catalyst?
Correct. Well done. Now, these things here, temperature, these will generally shift the position of equilibrium.
Yeah.
Okay. Because why this will shift the position of equilibrium? Because reactions are either endothermic or exothermic.
Yeah.
So if the forward reaction, this forward reaction was exothermic, it means that this reverse reaction would be endothermic.
Yeah.
And vice versa. How do we know whether the forward reaction would be exothermic? Well, if you are given a reaction and they give you some value next to that reaction written, and they give you minus 50 kilojoules per mole, the minus signifies an exothermic reaction. Okay. So this would mean that the forward reaction is exothermic. Now, they're not going to tell you that the forward reaction is exothermic. They're simply going to write the reaction and then put the enthalpy change that is associated with that reaction. What they're referring to here is the forward reaction all the time. The value given is for the forward reaction. So therefore, in the endothermic direction, the amount of energy that would be absorbed in this direction would be plus 50 kilojoules per mole. Okay, in the endothermic. So if you change the temperature, so for this particular reaction, if you increase the temperature, well, this system is going to want to what? Decrease that increase that you're affecting. So instead of going into the exothermic or forward direction, because the exothermic releases heat, that would increase the temperature, it's going to go into the what? The reverse direction, so that heat you're supplying to that reaction vessel can be absorbed. So it wants to restore back. Okay. So these are going to, so temperature is going to affect the position of equilibrium, and the position of equilibrium will shift to counteract whatever change you're effecting. And that will depend on whether the forward reaction is exothermic or endothermic.
Yeah.
Likewise, concentration. We looked at concentration already. If we said if you increase the concentration of A, then the forward reaction would be favored because the reaction is trying to decrease this effect that you have applied on the reaction, which is increasing the concentration of A.
Yeah.
Likewise, surface area. Now, surface area, this involves reactants which are in solid form. Affects solids. Okay?
Yeah.
So surface area has the same effect as changing the concentration. Likewise, pressure has the same effect as changing the concentration.
Yeah.
Now, what does a catalyst do in a reaction? A catalyst simply lowers the activation energy. And can you remember what the activation energy is?
Is it the amount of energy needed to is it to start the reaction?
Yes, minimum energy. The minimum energy needed for reaction to take place. Now, this lowers the activation energy, so not as much energy. So in other words, reactants, even with lower energy, then get a chance to react.
Yeah.
So there's normally a profile that you would have seen.
Yeah.
So this would be for an exothermic reaction.
Yeah.
This would be progress of the reaction. Progress, of reaction. And this here would be energy or enthalpy. And of course, the activation energy is this part. Okay?
Yeah.
Now, this is for an exothermic reaction. Can you remember what it looks like for an endothermic reaction?
Is it so the two lines that the curves that connect to the curves are the opposite way, like the opposite height?
Like that. Good.
Yeah.
Okay. And which one now is the activation energy here?
Is it all the way up?
Correct.
Yeah.
Okay. Yeah. And activation energy is sometimes denoted EA.
Yeah.
That's the symbol for it. That is EA. Right. But the EA in this case, and this here would be for an endothermic.
Yeah.
Okay. Now, a catalyst does not change the position of equilibrium. It simply increases the rate at which equilibrium is achieved.
Right.
So equilibrium is achieved much quicker.
Yeah.
But the position is still the same.
Okay.
Does that make sense?
Yeah.
Very good. So this simply here, please note, does not affect equilibrium position. Sorry, I've had to abbreviate that and cut it short just to fit everything in there. Okay.
Yeah.
These are sort of the main ideas that we work with when you are looking at these reactions. So far, so good?
Yeah.
Okay, good. So that was just a quick recap. And then now we can have a look at some questions. We're going to go through some multiple choice questions, and then we can have a look at some long structured questions, depending on time. But if we don't get time, you'll still be sent those with answers, so you can have a go at doing those as well. All right.
Yep.
Good stuff. Rightio. Waiting for this to load. It's taking a long time. I hope it doesn't crash. Ah, good. And I'm just going to save this because that was not a very good sign. Let's save that. Good. Okay, starting off with number 1.
Is it hydrated?
Definitely is hydrated. Good. So it's at the
And
C or D.
is it reversible?
It is reversible indeed. Okay, good. Next one.
Is that one hydrated as well?
Yep, correct.
Is it non-reversible?
Okay, so it says steam
Yeah.
and a blue solid are produced when pink cobalt 2 chloride crystals are heated.
Yeah.
With the addition of water to the blue solid, heat is
yeah.
released and the blue solid
Okay.
turns pink.
So it is reversible.
It is indeed.
Is it? Would it be combustion of propane?
Correct. Would this be reversible if you did it in a closed vessel?
Wait, combustion of propane?
Yeah.
I think so.
Not quite actually, because if we combust propane, remember what the products are. We get, what are the products? Can you remember? So this is complete combustion, by the way.
Is it water?
Yeah.
And is it oxygen?
Not quite, because this oxygen is a reactant.
I can't remember.
It is carbon dioxide.
Oh yeah.
Okay.
Yeah.
Plus energy if you're writing a word equation. So remember, all hydrocarbons during complete combustion, they form water and carbon dioxide. All hydrocarbons. If it was incomplete, then you would have carbon monoxide. And if it was very incomplete, then you would have carbon.
Okay.
And these two reactants would never ever join and nor to form propane.
Yeah.
Yeah. Okay. Good.
Yeah. Is it A?
Okay. So you've gone for zinc plus copper sulfate, forming zinc sulfate plus copper. This here is actually known as a displacement reaction. Okay. And it is not reversible.
Okay.
Sometimes also referred to as a redox reaction.
Okay.
Now, do you know what B is representing?
Is that a plus between the CuSO4 and
No, it's a dot.
so are they multiplying?
Not quite in this case. This is simply saying these are, and it's worth to know what this notation means. These are hydrated
Okay.
copper sulfate crystals.
Yeah.
Okay, so this here would be anhydrous.
Right.
Anhydrous meaning water has been removed from it.
Yeah.
So which of these reactions, looking again, do you think? Think back to the questions you did, question 1. Think back to question 1. Give you a bit of a reminder to help you. Here it is. Same reaction they're talking about. So now, which of the following reactions is reversible?
Is it would it be B?
Correct. Okay, and this is a common one. The other common one that will come up and crops up in AQA as well, another common one worth knowing is this one, cobalt 2 chloride.
Yeah.
So these are very common ones. These are reversible reactions, as well as this reaction there. Oops, I'm getting a phone call. Sorry, Raheel. So you're absolutely right there. It would be B. Okay,
Yeah.
good. Next one.
Is it 1 and 2?
Sorry, Raheel, which one did you go for?
Is it 1 and 2?
1 and 2. Okay, so 1 and 2. Can you give me the reason why you went for 1 and 2 on that one?
I thought it's just like to go back to the other.
Correct. We're just going back. You're absolutely right. Good. Well done. Okay. Next one.
This is what I was confused on, like the conditions.
Yeah, not to worry. So have a little think. Have a little try. Don't worry about making a mistake. And then try and just talk me through why you think the answer you select is the correct answer.
Would it be D?
Not quite on this one. So let's just try and think about this one because it is a bit tricky. Yeah. So carbon and steam. So I've got a gas, okay, but a solid. So these are going to be affected by pressure, aren't they?
Yeah.
Yeah. So if we just try and look at the number of moles, well, firstly, is this balanced? Yes, it is. So checking if it's balanced is also very important. Generally, the examiner is not trying to trip you up on questions like this. So they'll generally give you a balanced equation, okay?
Yeah.
But look at the marks. If there's more marks than 2 on a question like this, asking about conditions, then you may possibly have to balance the equation. but this is balanced, so we're okay. But it says carbon and steam is reacting. Okay, carbon and steam are reacting. So this side is the hotter side of my reaction. So this reaction, okay, it would help if you know that the forward reaction is endothermic. So this forward reaction is endothermic.
Okay.
So if we know that the forward reaction is endothermic now, let's just check. I've got 1 mole of gas here, but I have 1 mole of gas there and another mole of gas. So this side of my reaction, I have a total of 2 moles of gas. So which side do you think has a higher pressure? The left-hand side for the same volume or the right-hand side?
The right-hand side.
Correct. There's more gas than, more gas on the right-hand side in terms of molecules than on the left-hand side. So now it says, which conditions of pressure and temperature would provide the highest yield of H2? So we want to produce as much hydrogen as possible. Yeah?
Yeah, so
we're just going to write on this side, we're going to say this side is high pressure.
Yeah.
Just so we can picture what's going on better. And this side is low pressure. So now this is the condition of the vessel. This is inside the vessel.
Yeah.
If I try to then increase the pressure, which direction is this reaction going to want to go to? To the right-hand side where there's high pressure or to the left-hand side?
To the left-hand side.
Correct. And if I go to the left-hand side, I'm not going to get as much hydrogen, am I?
Okay, so
it's either A or B. Because if I apply low pressure, you know that this reaction is going to go to the direction of high pressure. And in the direction of high pressure is my hydrogen.
Yeah.
So you're happy with the fact that it's got to be a low pressure.
Yeah.
Whatever the case.
Yeah.
What about the temperature? Well, it means that this direction here, so this is endothermic, but this going back this way would be exothermic.
Okay.
So if I increased, yes?
Yeah.
If I increased my temperature, which direction would it want to go? Would it want to go in the direction where it's exothermic or the direction that's endothermic?
Would it be, wait, if you increase the temperature?
Yeah.
Would it go to the endothermic side?
Correct. Because exothermic is going to raise the temperature even more.
Yeah. Okay.
And the reaction doesn't want to do that. It wants to counteract what I've just done. So it's going to go into the endothermic direction. Okay. And in the endothermic direction is my hydrogen.
Yeah.
So you're happy that the answer should be B.
Yeah. Okay.
Yeah. Good. Yeah. So it's always good with these ones to almost write it out a little bit and then really get the feel for what's going on as opposed to just jump straight into it.
Yeah.
Okay. All right. These ones are a little bit more on the challenging side now, Raheel. Okay, but they will give you more confidence and experience as to what's going on.
So it's a forward reaction exothermic.
Yeah.
So would it be a high pressure?
High pressure, good. So it's either C or D, good. You've made the
Uh,
right deductions.
And then would it be high temperature?
So think about it. Says that this reaction, this side, moving this side is
Oh,
exothermic. So this is, so the way I wanted you to think about exothermic, maybe that might clarify things in your mind a little bit, is think high temperature.
Yeah.
Okay.
Right.
And endothermic, which is this reaction, the reverse endo, I want you to think about it as low temperature.
Right.
So if you increase the temperature, it's going to want to go in the direction of low temperature.
Yeah.
Which is this stuff this side.
Right.
If you decrease the temperature, the reaction is going to want to go to high temperature,
Yeah. Right.
which is this side of things. So maybe it might help. Maybe your mind might intuitively think about it easier.
I just put the endothermic and the exothermic over the wrong side of the
equation. Right. Okay, I see. And maybe the part that confused you was carbon monoxide and steam react together exothermically. So you thought, okay, carbon monoxide, that, okay, so this is exothermically. They meant that side of things.
Right. Yeah.
No problem. So we for this one, did we say C?
Yeah.
Good. Number 2.
So is a forward reaction exothermic?
Is the forward reaction exothermic? You're right, because they have given us that level of detail, haven't they?
Yeah.
Good. That's there. Excellent.
Would it be B?
Did you go for B?
Yeah.
Okay. So let's have a look at this one again. Let me just reduce this.
It's I know it's it was N2O4 as well.
So which one are you going for?
I haven't read the other ones, but
okay. Have a go again. No problem.
Would it be C?
Think about this one again. Have another think about it. Not quite C. Have another think.
Wait, so so is the N2O4 decomposing to make 2NO2?
Yeah, it could decompose to that, but let's just work through this together a little bit. And I think maybe you may have some things already similar. You just tripped up on someone. So it says the reversible reaction between nitrogen dioxide and dinitrogen tetroxide is shown. Which of the following statements about the equilibrium mixture in this reaction is correct? Let's just look at the first one. If the pressure is decreased, by the way, let's just label a few things here, shall we?
Yeah.
So this is, we've said, if we just look at pressure and high pressure and low pressure, which side is high pressure, which side is low pressure?
The first side is high pressure.
Going this way? Or you mean this?
That one's high pressure.
Yeah, going this direction is high pressure. You're right. High P, and this side would be low P, low pressure. Because I've got 2 moles of gas, I've only got 1 mole of gas. There we go. Okay. And we've been told that this side increases temperature, this direction. This side decreases temperature. And I could have used the word endothermic, but it just might make the understanding of this a little bit easier. So if the pressure is decreased, the amount of N2O4 increases. And it's saying which of the following is correct. They want the correct statement, don't they? So is this statement correct? If I decrease the pressure, would the amount of dinitrogen tetroxide increase?
I thought it would go to the other side because
You're correct. It's going to want to go to the other side because this is where the high pressure is. So this is wrong. The question is saying which statement is correct. So we're choosing the correct statement. So this statement cannot be correct. Because we have said if you decrease the pressure, it's not going to want to go to where there's low pressure. It's going to want to increase the pressure back. So it's got to go to form this. So that's incorrect. If the pressure is increased, the amount of NO2 formed increases. Hang on. If you increase the pressure, it's going to want to decrease the pressure. So it's going to want to go to the low pressure. And in the low pressure is dinitrogen tetroxide. So this is incorrect as well. Following so far? Says the decomposition of N2O4 is exothermic. The decomposition, meaning when this breaks down into that. That's what a decomposition is.
So,
but it can't be because if this side is exothermic, this side must be endothermic. So the decomposition is endothermic, not exothermic. So this can't be right either. The decomposition of N2O4 is endothermic, and therefore our correct answer is D. Did you follow that? Okay, good. Number 3.
would decrease in the pressure be one of them?
Correct. So the first choice, so it's either B or D. Good.
So would I write endothermic over this the CO plus 3H2
Correct. So this arrow here
is
in the endothermic direction. This goes to the side of the reaction that lowers temperature. And this side here, moving that way, is the exothermic. So this side raises temperature.
Yeah.
Good.
So would it be increased temperature?
Correct. So what's your option then?
Was it B?
Correct. Good.
So is the forward reaction exo?
Correct, because we have the minus sign and that's representing the forward arrow.
Yeah, so I'll write that over the 2SO3.
Correct.
Right.
One moment, Ray. I won't be long at all with you. 2 seconds. Go on, Rahil.
Would it be 1 and 2?
Correct. You're spot on. Well done. Excellent.
How would I see about the concentration?
Okay, so decreasing the concentration of O2.
Yeah.
What if you decrease the concentration of O2?
Yeah.
Yes. What's the reaction going to want to do? Let's answer that question first.
Oh, of O2. Oh, so it will the. Oh wait, what?
So if I decrease the concentration of O2, what will the reaction want to do?
Increase.
Correct. And the only way it can increase it is by breaking this down.
Oh, okay.
So it can form that. That's the only way O2 can be increased, by breaking the amount of sulfur trioxide and decomposing it into these two products.
Yeah.
Okay. So it definitely cannot be 3. We want to increase the SO3. If we decrease the concentration of that, this is going to break down. We're going to decrease.
Yeah.
Yeah, that makes sense now?
Yeah.
Good. Okay, question 5.
Is it A?
You are spot on. And this brings me to have a bit of a discussion point here, because students, now here it's multiple choice, so the answer is given, so you can rule out the ones that are there.
Yeah.
But a common mistake for students is to think that at equilibrium, the concentrations are the same of both the reactants and products. No, they are not.
Yeah.
It just means that if I have A, I'm going to just make this easy, breaking into B plus C, okay? So at equilibrium, you may have a concentration of A, which is 2 moles, the concentration of B, which is, well, concentration really, I should be saying moles per decimeter cubed, shouldn't I, if it's concentration. This may be 3 moles per decimeter cubed, and this may be 2 moles per decimeter cubed. And that will be at equilibrium. Now, they're not the same, they're not identical. It just means that these concentrations stay fixed, they don't change. And that is why it is saying equilibrium refers to the concentration of reactants and products relative to one another.
Yeah.
That's why it makes that statement there. Okay,
Yeah.
good. So just not to confuse it, especially when defining equilibrium, do not say that the concentration, yeah, you can say that the rate of the forward reaction is equal to the rate of the reverse reaction, but the concentrations, of course, will remain the same.
Yeah.
Yeah, the concentrations relative to one another remain the same. Okay, number 6.
Would it be B?
So you've gone for B for that one?
Yeah.
And you are absolutely spot on. Good.
Would it be C?
It would indeed be C. Good. Number 8.
Is it? Is temperature one of them?
Temperature will be one of them indeed.
Pressure is.
If they are gases,
Yeah. So wait, does that count as one then?
yes, because it doesn't specify it.
Yeah.
Whether it's
so,
a gas reaction or whether it's solid does not specify.
So if it for solids, would it be so 2? Would surface area be for solid?
Surface area for solids. Okay, now this here can be a bit of a tricky one. So in other words, this one here will affect the reaction rate.
Okay.
It will affect the reaction rate, but similar to a catalyst, has no effect on the equilibrium position.
Okay.
This is a tricky one.
Yeah. So,
but it's just like a catalyst.
So it would be 1, 3, and 4.
Correct.
Yeah.
But remember this one, just as you will
Yeah.
for a catalyst as well. Next one.
Would it be B?
You're spot on. B for this one. Correct. So you have taken on board that point I made. Good. Okay, right. So really good. We have sort of covered all the fundamentals really that you need to be able to answer long structured questions confidently. And the key thing here is just a little bit of practice still needed, especially where we've got endothermic and also involving gases, just so you're more certain on what's going on there.
Right.
So I'm not going to bother start the long structured questions, but I will email them to you with the video, and you can go through them and then have a go at marking them as well. So I've deliberately chosen grade 8 and 9 questions. So you will find them extra challenging, okay? But there's no harm in that because you will then build your confidence more from there. What also I've done is I've included examiners' reports as part of the document I've sent you. Now, the reason why I want you to start looking through examiners' reports is because I want you to start noticing what the common mistakes students make. That is what the examiners' reports contain. That way, you know what mistakes not to make when you're answering those long structured questions. Okay. Yes, good. Okay, so in terms of next lesson, again, we said we're going to be sticking to the roadmap, or in other words, the topics that were listed. Is there any topic from, any subject really of the sciences and maths that you kind of think, okay, I could do with going through some rigorous questioning or working through exam questions with that? Any particular topic that comes to mind?
I think there might be. There was something that we were doing in maths today that I can't remember what it was, but I struggled with it.
Okay.
So I think I'll check that.
Check that and then let me know what it is. So maths. So we're going to say new topic at school.
It wasn't a new topic. We were just revising something. So
Oh, but you haven't done it in a while and you just felt a bit
yeah,
rusty on it. Oh, got you. Because I think you did tell me that you'd finished all the topics in
yeah,
maths, isn't it?
yeah.
Okay. So this is just going to be a recap. And we're going to say topic to be confirmed.
Yeah.
Okay. Next lesson then, Rahil, have you thought about when you'd like to have the next lesson?
Could you do? I don't think I can't do Friday or Saturday.
Okay. So Sunday?
Yeah. Could you do Sunday?
Yeah.
Could
So
we?
we're gonna go for Sunday. If we go for what time did we start last time? 4 p.m.
Yeah, that's fine.
Would that work for you?
Yeah.
Brilliantos. Okay, and that brings us right to the end of the last minute
Yeah.
of our lesson today. Then I shall
Yeah.
see you on Sunday at 4 p.m. And
Yeah.
just text me before then, and then I can get all the past papers and stuff we need so that we can get you feeling in a better place with that particular topic.
Okay.
Okay,
Yeah.
good stuff.
Thank you.
Well, you have a lovely evening. You're most welcome. And do some homework as well when you get a chance, especially while the concepts are fresh. You don't need to go through the whole paper here, even just one or two. I know you've had a long school day, but even if you just said, look, I'm going to try and do one question to do today, do another one tomorrow, to me, that's fine. Okay. And one question shouldn't take you more than 20 minutes anyway. But you deserve a little break for the meantime. Okay, let your brain rest a little bit, and when you're ready, have a go at those questions. And if there are any problems, just let me know on Sunday as well. Okay.
Thank you.
Okay, no problem. Most welcome, and see you then. Cheers now.
Bye.
All right, bye now. Bye.